All right, you're watching Industrial Electronic Devices Lecture 2 on series circuits. So what I'd like you to do is stop the video, pause the video, and draw this and try to solve it. Once you've done that, work through all your numbers, restart it, see if you get the same numbers as me. I'm going to introduce a new formula here today called the voltage divider formula. So try to solve it yourself. You've got all the information that you need, and then restart it and see how it's going. Okay, to start this off here, what I want to do is I want to say, okay, well, there's a couple ways to do this. We can start by finding the total current in this circuit here, and we know what the total resistance is, and the total resistance is going to be, in a series circuit, is just simply the sum of the individual resistors. So we got 3, 4, 5, so we got 600 ohms of resistance in this circuit. And we could find our total current by just using Ohm's law. We could say the total current is the voltage divided by the resistance. So, you know, my IT equals my ET over my RT. So 120 volts divided by 600 ohms is 0.2 or 200 milliamp. So we got 200 milliamp in there. It's going to get rid of that. So, but we know it's 200 milliamps, so I'll put 200 milliamps back in there. Okay, and we could even finish these totals off. We could say, okay, well, my power total, using Watt's law, my power total is my voltage times my amperage. 120 volts times 0.2, not 200 milliamps, is 0.2, is going to give me 24 watts. 24 watts. So in a series circuit, the sum of the individual power dissipations, P1, P2, P3, must equal PT. So that's a check for us. The sum of the individual voltage drops, E1, E2, E3, must equal the total voltage applied. And because it's a series circuit, the current must remain the same. There's only one route, there's only one path for that current. It has to go through all of these and then goes back to source. So the current must always be the same. If the current's all the same and we know that we've got 200 milliamps, we could write 200 milliamps all the way through. Each one of these has the same amount of current flowing through it because there's only one path. All right. So we didn't need to have this information here in order to find the voltage here. We could use something called the voltage divider rule. The voltage divider rule looks like this. It says the voltage at a particular resistor is equal to the resistance of that resistor divided by the total resistance times the total voltage. So let's punch these numbers in here. So we could say that the voltage at 1 is going to be equal to the resistance of 1 over the resistance total times the total voltage. So if we look at that, we've got the voltage. We've got resistor 1 is 100 ohms, divided by the total resistance is 600 ohms, times my total voltage of 120 volts, gives me a total of 20 volts. So I'll write that in there, so 20 volts. So now we go, okay, well, is that right? Well, if we used Ohm's law to find it, we know we have 200 milliamps. We say, well, E equals I times R, and E is going to be equivalent to my amperage, 200 milliamps, or 0.2 of an amp. 0.2 times 100, yeah, sure enough, gives me 20 volts. So that's right. Let's take a look at this one here. Let's use Ohm's law for this one here. We can say that E2 equals I2 times R2. And E2 would be equivalent to 0.2 of an amp times 200 ohms. So 0.2 times 200, we get 40 volts. 40 volts. Notice that we've got 100 ohms here, current's the same, 200 ohms here, and a double in voltage. So the voltage is doubled as a result of a doubling of the resistance in the circuit. So that makes sense. Let's do E3 here. E3, same thing, equals, and you can use a voltage divider rule, you can use your current, whatever you like. So we're going to say, well, that's 0.2 times 300, that's 60 volts. So we got 60 volts there. Let's take a look here. If I go, okay, so the voltage from here to here we know is 20 volts. But what is the voltage from here to here? Well, that's going to be 40 plus the 20, which is 60 volts. So we didn't even have to find this out. We could have just said, well, I know I dropped 20 there and I dropped 40 there. I only have 120 total. So this must be 60 volts from this point here to this point here. It must be 60 volts, and of course it was. So if we look at our voltages, we've got 20, 40, 60, 60 plus that is 120, so it works out. So that's what we're looking for. That's our check. Let's take a look at our wattage here. We know we got a total of 24 watts, and each one of these individuals, each one of these will dissipate a wattage, and the sum of those wattage dissipations must equal 24 watts. If it doesn't, we've done something wrong. So let's take a look. I'm just going to erase all this here. Let's take a look at our power. So power at 1. Well, we see power at 1. We're going to use the watts triangle here. Watt's law, power is equal to voltage times amperage. So power 1 equals E1 times I1. And E1 we know is 20 volts. We just calculated that. R1 is 100 ohms. Oops, 0.2. What am I doing? So amperage, 0.2 of an amp. There we go. So if we calculate that, 20 times 0.2, we get 4 watts. So I got 4 watts here. Let's do P2. P2 equals E2 times I2. And E2 is 40. I2 is the same thing, so 0.2. And that gives me 8 watts. So I get 8 watts there. I got 8 here and 4 there, which is 12 watts. And I got a total of 24, so this must be 12. Let's check that out. So P3 equals E3 times I3. So I've got 60 volts times 0.2. 60 volts times 0.2 gives me 12 watts. So I've got 12 watts here. I got 12 plus the 8 is 20 plus the 4 is 24. That matches our 24 there.